language itself.
So as mentioned before the camera started rolling, master sets for 7 and 8 are due in 1 week. And we're about to start chapter 9. Any questions? All right. Now, think about the number of equations we've dealt with up till now.
Too many. Too many.
Well, we're about to double that number. So, it might seem daunting at first, but it's really not as bad to double the number of equations. So, we have been dealing with linear or translational motion. Linear is the term that I've been using, but translational it means the exact same thing. So linear momentum and translational momentum, there's no difference. Typically, which one you use depends upon just tradition.
I'm sorry, backtracking. What is chapter 9 about?
Rotational motion. Or angular motion, depending upon which one you do, because that's what I'm going to write. About to write over here, we have rotational or angular motion. And whether you use the term rotational or angular, typically as tradition, you tend to talk about angular velocity instead of rotational velocity. But if you're among a bunch of physicists and you said rotational velocity, they know exactly what you're talking about. They probably think that you just had some instructor who called it that, and that's why you called it that, but they would not look down upon you. All right, so for each of these, there's some analog over here. So for example, position. Which we use X, Y, Z, R, S. The rotational analog is angle. Now the typical symbol used for angle are the ones that I've been using, theta, except we'll put a vector symbol over it now. Theta, phi are the two most common ones, but there are other ones that can be used. But I'll just stick with those two for now. Displacement. The symbol, just stick a delta in front of whatever you're using for position. And over here, officially angular displacement. And it's just going to be delta, theta, etc. However, typically a problem's not going to ask you for angular displacement. It's within the context. Typically, if I have a wheel that's rotating, the wording would be, through what angle does it rotate? So that's asking for angular displacement. Velocity, angular velocity. And the symbol used for angular velocity typically is an omega. This is an omega. It is not a W. We use W for too many other things. It'd be really nice if we could stop calling it a W. It's a dream. Acceleration. Anyone want to take a shot at what it's called, the rotational analog is?
Centrifugal acceleration?
Nope.
Angular acceleration.
That's the one. So if I have something that is going around in a curve, if the speed is constant, then the only acceleration is centripetal acceleration. But if the speed is not constant, then I have angular acceleration also. So that deals with the rate at which the rate at which something is rotating. If that changes, that's what angular acceleration is. So it will allow us as an object's rotating around a circle, getting faster as it goes, we can now look at both. And the symbol follows along a pattern that shows up often is the fact that the thinking is they look at the word acceleration, or probably for the Latin, acceleratio or something like that. They think, what Greek letter starts with the same letter? And they go, oh, alpha. So they use alpha. And what is the angular or rotational analog of time?
Time.
And indeed it is. Yeah, time doesn't care how you're moving in classical physics. Now there's going to be more to this list, but at least this is enough for us to show how we're going to double the number of formulas. So if I take one of the cake formulas, let's say Vf equals Vi plus At. The rotational analog of it holds. All we have to do is transliterate, so that becomes omega F equals omega I plus alpha T. So I have something that is spinning. So I take my wheel and I rotate it. It's going to slow down eventually because of friction. So there's a change in angular velocity. So I take my initial angular velocity, figure out my angular velocity sometime later. I can figure out my angular acceleration by just plug and chug. Just pick another one. Displacement is equal to VIT plus 1/2 AT squared. What would be the rotational equivalent of this?
Angular displacement.
Yeah, angular displacement is equal to omega initial time plus 1/2 angular acceleration, or the alpha
Yep.
T squared.
There's a plus sign in between. So now let's do a couple others. Force. The rotational analog of force. Force is an influence which might cause acceleration. The angular one is an influence that might cause angular acceleration, clever the way they came up with it, and it's called torque. The symbol typically is tau. And in what used to be my most obscure reference, you might also call this G2 kombucha. I had only one student ever understand that reference. And the shocking was, he knew it because he had listened to stories his dad had told him. Which is a lesson for my kids. They should listen to the things I tell them. I don't know your dad, so I don't know whether you're listening or not. Mass. So mass is a measure of inertia. It's a quantification of inertia. So the bigger the mass is, the harder it is to change it's doing whatever it's doing. Rotational, we want something that wants to resist the effort to rotate something, and it is called moment of inertia. It actually has two names. Moment of inertia is what I typically call it. And some textbooks will call it rotational inertia. And this is when they get away from the Greek letters for the rotational things. The symbol typically is just a capital I. It is a scalar, just like mass is. And we'll get into how do you actually calculate moment of inertia.
Is it related to mass?
It is,
Okay.
but it's also related to where mass is positioned. I'm looking for, there's a blue tube and a red tube. And I'm not seeing these things here. Is that the way in here? Okay. See if I can track those down at some point. Oh, no, somebody actually put them in the box. These are two objects that have the exact same mass. The only difference is where the mass is located. And you can sort of tell that this has a hole in it right there, that you should be able to see all the way through, where this one, you can see all the way through here. So in this one, the additional mass inside is located really close to the center, and this one is located farther away. I'm just going to zip them back and forth real quick, and I think you can easily tell the difference. So that is an indication this has much lower moment of inertia than this does. It's much easier to change its angular velocity than this is. And of course, we'll get into more of that later. So if I take Newton's second law, F equals ma, what would be the rotational analog?
Torque times angular acceleration.
Wait, say it again?
Torque times angular acceleration. So
You left some stuff out of that.
Oh, wait, hold on. Oh yeah, I did, sorry. Torque is equal to the big I, moment of inertia, times angular acceleration.
Yep. And just like this is the total force, this is the total torque. Individual torques we'll get to. I know that momentum is equal to mass times velocity. Angular momentum is angular momentum. Is equal to
Moment of inertia
Yeah.
times
Omega.
omega.
L equals I omega. And the last one, before we actually start doing something more with this, rotational kinetic energy.
One half I times omega squared.
Now, when we got to kinetic energy, and I had said that was the formula I had to memorize, my reasoning was that that formula stays the same. It's 1/2 mv squared. It doesn't matter if you're working on your Nobel Prize winning dissertation or you're working on in this class, it's still 1/2 mv squared. And yet I am throwing them, hey, wait a second, there's another equation here for kinetic energy. The difference is 1/2 mv squared is at the heart of this, but how do you deal with the kinetic energy of an object where not everything is traveling the same speed? All the examples we've done before, an object is basically in translational or linear motion. Every part of that is traveling at the exact same speed. But if I have something rotating, not everything is traveling at the same speed. And so when we make that bridge from 1/2 mv squared into this, that will demonstrate what I actually is when we get to a more formal math definition of I. Right. Questions before we start talking about the directional piece of these vectors? All right. So I take this wheel and I spin it. It is rotating about some axis, so it has a rotational velocity, that's not zero. What is the direction of the velocity?
Towards the center?
That would be the centripetal acceleration. But the angular velocity,
Tangential to the circle?
pardon?
Is it tangential to the circle?
So which tangent, which direction?
Clockwise?
I
I guess that's instantaneous.
thought it was going counterclockwise. Say it again, Amy?
Clockwise to me, but counterclockwise to you.
Man, that's gonna get really wordy if we have to throw that into every time. I have a wheel spinning. It's counterclockwise to people standing in this part, and it's clockwise to people standing in this other part. But ultimately, if all of us are looking from the same point of view, we can get away with clockwise, counterclockwise. The trouble is, exactly for this reason, we're not all standing on in the same area in order to be able to make that judgment. So the powers that be came up with a way of denoting the direction it is spinning, which is independent of the observer. It is one of many right-hand rules. Yep, it is not the dominant. Anyone left-handed in here? Okay, so we don't have to worry about that. All right. Left-handed people, it's still the right-hand rule. But, so we have an axis here that's basically front of the room, back of the room, or back of the room, front of the room, either one. So the thumb is basically gonna be positioned along the axis of rotation, which means my thumb's either pointing towards the front of the board or to the back of the board, or the back of the room. As this spins, I want my fingers to curl in the direction that it's spinning. So obviously, that doesn't work particularly well because my fingers are curling opposite the direction it's spinning. My fingers curl that way. My thumb points in the direction of the vector. So my angular velocity is to the front of the room. Now, when I was first dealing with this as a physics student, I got really confused because I kept thinking, what is going towards the front of the room? Nothing physically is going to the front of the room. It is just a notation to indicate that the angular velocity is going around like that way. So if I said, all of you were out of the room, and I said, I have an object that is spinning with the angular velocity towards the front of the room, ideally, all of you would go, say, to the front of the room, therefore it must be spinning around like this, regardless of where you're standing. If I close that door, what would be the direction of the angular velocity?
To the ceiling?
Yes. Thumb acts what is parallel to the axis of rotation, or the axis of rotation at the hinges, which are running vertically. The door is going to be closing around like that. My thumb points up. If I open the door, the angular velocity would be down. And again, nothing is physically going up or down. It is just the notation that's used to indicate the direction of these vectors.
Wait, can you say that? Like, how would you word that? What way? How would you word that in a problem to?
A door is swinging so that the angular velocity is
To the ceiling?
up
Okay.
or out of the page. Depends on if you're looking at a piece of paper with a problem, like it could be coming out of the page.
Okay.
Can you give another example? I wanna try and see if I can, of angular velocity.
Let's see. Try to think of something that's actually different. All right, so I have this right here. I'm gonna let it fall. Let's see which way it's gonna fall. So, as it was going down, the axis of rotation was basically at the end, the point that wasn't moving, or close to it. And so therefore, the angular velocity, well, that's the axis right there, and it's swinging either this way or this way, so my thumb's either pointing towards the front or towards the back. And so, in that case, it was falling that way.
Oh, okay, yeah, that makes sense.
Is that sufficient for now?
Yeah.
So let's do a quick problem here. A car is driving. You know, at most of my life, a car is driving would be just really bad English because a car doesn't drive itself, but nowadays it works. Driving along a straight road with initial velocity of 5 meters per second. It accelerates at -3 meters per second squared for 10 seconds. What is its displacement? The chapter 2 problem. And now a chapter 9 problem. A wheel rotates. Along an axis with initial angular velocity of 5 radians per second. It has an angular acceleration of -3 radians per second squared for 10 seconds.